Okay, basic design and theory in design the heat exchanger. Okay, before we proceed to the detailed design, we learn about the basic design and its theory. Okay, what is the theory behind this designing the heat exchanger? Okay, the concept is based on I believe that you are familiar with the equation Q equal to UA delta Tm, which is heat transfer or Q. The unit is in watt, and the U is the overall heat transfer coefficient. Usually we can refer to the diagram, to the reference table, and then we may start the initial guess the value of U first, and then after that we may calculate the error, the percentage of error, whether the estimation or initial guess of the overall heat transfer coefficient is correct or not. And then after that, we need to identify the heat area transfer and also a log mean temperature, and also the mean temperature different or denoted by delta Tm. Okay, the main objective of this theory in designing the heat transfer is to determine the surface area required for the specified duty rate of heat transfer using temperature differences available. So this is equation to determine the overall coefficient that we can compare this calculation to the initial guess before we can proceed to determine the surface area. So we can see here in determine the overall coefficient, it basically we require the inside and outside fluid film coefficient, which is covered the tube and also shell part. Okay, these are the table that provide the information on the value of U or overall heat transfer coefficient. If based on the shell and tube, so we can determine the coefficient whether it is hot fluid or processed fluid, or if we use the coil immersed into the shell. So you can use this range. Example, your hot fluid or using hot water. So you may use the range of the U is based on from the 800 to 1000, 1500. So followed by other type of the hot fluid. Or if your processed fluid or based on the air-cooled exchanger. So if we use the cool water, you may use this range to estimate the value of overall heat transfer coefficient. So you may refer the table from table typical overall coefficient from this reference book. Otherwise, we may refer to this diagram that applicable for shell and tube time. So example, if we use cooling water and then our second fluid in the related to the processed fluid coefficient is the oil. So basically you may drag this, okay, cooling water, you may drag to this, and then we can estimate the value of U. Okay, these are the steps in a typical design procedure. We start to define the duty, heat transfer rate, flow rate, and temperature. And then second, we need to define the required fluid physical properties, including the density, the viscosity, and thermal conductivity of each fluid. And then after that, we need to decide the type of heat exchanger before we can set a trial value for the overall coefficient or U. You may refer to the diagram or table to set the trial value. Then after that, we may calculate the mean temperature difference, and then we can calculate the value of area here, because we have the Q here after you. Q can be obtained after you perform the energy balance, and this is from the trial value that you can obtain from the diagram or the table, and this is from your calculation. And then after that, we may proceed to the detailed design. Okay, by decide the exchanger layout, including the number of tube, bundle, and shell diameter. I will explain to you the detail about this later. And then we can calculate the individual coefficient in the inlet for the tube and also the outlet for the shell, and then calculate the overall coefficient using the calculation that I showed to you previously, and then compare with the trial value. If the calculated value differs significantly from the estimate value, usually should be not exceed than 30%. You can substitute the calculation for the estimate value and return to the start seat. If more than 30%, we need to perform or return to the start seat here. We need to apply another trial value until we can obtain less than 30%. And then after that, we may calculate the passenger pressure drop. Okay, after we have done with the overall heat transfer coefficient, we may proceed to the pressure drop. Okay, if unsatisfactory, return to the step 7, 4, or 3 in order of the preference. And after that, we can optimize the design. Okay, how can we optimize the design? Based on the cheapest heat exchanger. Basically, the lowest or the smallest area, we can choose the smallest area or give us the cheapest exchanger.